this video, we're going to introduce the concept of a vector and some of the concepts that go with it. So I want to preface all of this just by stating that, of course, vectors, the idea of a vector, that's a very, very complex, very broad kind of topic. So we're just going to deal with some of the basics in this video. You're going to look at vectors in more detail in calculus. Vectors are also used very often in a physics kind of situation. So if you take a physics course, you'll also talk about vectors in more detail, some of the uses and some of the mathematics behind using vectors. So first off, what is a vector? So in physical situations, we typically use two different kinds of quantity to describe what we're going to think of just in terms of motion, something that's moving. Okay, so a scalar is one type of quantity that only describes magnitude, which is the technical term for amount. So the amount of motion. So in magnitude or amount. So for instance, if you think about driving in a car, we can talk about the car's speed, how fast the car is traveling, so miles per hour, something like that. Now a scalar can be altered in order to create a vector. So a vector is a quantity that describes both magnitude, so the amount of the quantity, and direction. So it's an amount expressed in a particular direction. So the vector associated with the scalar speed is velocity. So velocity is speed in a particular direction. So graphically, when we're talking about something that represents a vector, something that has both a magnitude, an amount, as well as a direction, typically we represent a vector graphically as a line segment, specifically a directed line segment. So it's a line segment with a specified direction, and the direction is indicated both by the slope of the segment as well as an arrow. So the arrow will indicate where the segment starts versus where it ends. So the slope is going to indicate a direction, and the arrow is going to tell us where we start versus where we end. So this is an example of what a vector would look like if we were to graph it. So P is what we call the initial point, and Q is what we call the terminal point. So one notation to indicate that we have a vector that starts at this point P and travels to this point Q, a certain distance away, traveling in this particular direction, is the following notation. So we'll write the label for the initial point, for the terminal point, and then we draw an arrow over top. Now vectors can also be denoted typically when we type them using a bold letter. We can't really bold if we're just writing in pen or pencil, so we're always going to use the arrow notation to show that we're talking about a vector. And again, P, where the vector starts, is what we call the initial point of the vector. And Q is the terminal point of the vector. Now, if we want to talk specifically about magnitude, the magnitude is going to be the length of this segment. And the notation for magnitude, it's going to look very similar to absolute value notation, except we use double bars. So double bars, and then we write the name or label for the vector inside the double bars. And again, this represents the length of the vector. If we're thinking graphically, it's the length of this line segment. That is the amount that this vector happens to represent. So let's talk about how we could actually represent a vector when we have real quantities. So one form for representing a vector is what we call component form. So component form allows us to break down the vector, the whole amount, the whole quantity, into components. So specifically, the components represent how much horizontal and how much vertical displacement occur in order to travel from the initial point to the terminal point. So if we think of starting at P and traveling towards Q, we travel a specific horizontal amount, and then we travel an additional vertical amount, and that takes us from P to Q. Each of these is considered a separate component of the vector that takes us from our initial point to our terminal point. So if we have the coordinates in the coordinate plane for where the initial point and where the terminal point are going to be, we can use these values to find the horizontal and vertical components of the vector. So you'll notice the notation we're using here is an angled bracket. We don't use this notation very often. This is pretty much specific to vectors, but this notation is going to be able to indicate that we're not talking about an ordered pair, which is given in parentheses. We're talking about a vector, which indicates some type of motion from one point to another. So the horizontal component of our vector, the first component, is going to be the difference of the terminal point's x-coordinate and the initial point's x-coordinate. In other words, it's the amount of displacement that it would take to get from the first point to the next point, horizontally speaking. Now, it's always going to be the terminal x-coordinate minus the initial x-coordinate. And then same thing for the vertical component, except it's going to be y2 minus y1. And this, of course, is assuming that we know the coordinates for our initial and our terminal point. Now, one thing that's important to keep in mind is a vector is independent of position. So in order to write this component form, we do have to have an initial point and a terminal point. But if we knew the component form of a vector, then we can take that vector and we can move it around in the coordinate plane and it doesn't change the vector. So in other words, if you were to imagine taking this vector with its current initial and terminal point and just translating it somewhere into the coordinate plane away from where it's currently located, it still represents the same vector. As long as it has the same length and the same slant and the same direction, in terms of we start at one point and we end at another point traveling in that particular direction, we can relocate it to other points within the coordinate plane, different initial and terminal points, and it still represents the same vector. Now, typically we're interested in vectors in standard position. They're going to be easiest to use to represent actual situations in application. So a vector in standard position, just like an angle in standard position, has an initial point at the origin at 0, 0. So let's do a little bit with vectors graphically and using their component forms. Okay, so suppose our vector has an initial point at -2, 1 and a terminal point at 2, -5. So first thing we want to do is find the component form of this vector v. Now you'll notice here v is bold in type, but when we write v, because we can't really bold, we're going to have to put the arrow over it in order to indicate that we're talking about a quantity representing a vector. So we want to find the component form of the vector that would take us from this first point and travel to the second point. So v in component form, our first component is going to be our horizontal displacement. So in other words, how far we have to go to get from our first x-coordinate to our second x-coordinate. And that's going to be defined as x2 minus x1. So watch your signs here. We're subtracting them, but we're subtracting a negative coordinate. Now our horizontal displacement, similarly, it's the distance to get from our initial y-coordinate to our terminal y-coordinate. So in this case, it's going to be -5 minus 1. And so we simplify those two values down, and that's going to give us the component form of our vector. So 2 minus a -2, that's going to be 4, and -5 minus 1 is going to be -6. So once we have the component form, this vector is now independent of where it started and where it ended. In other words, we could choose any initial point we want, and using these values, which tell us how far to travel horizontally and vertically to get to a terminal point, we could then move that vector anywhere in the coordinate plane and give it any initial point. So that is going to be our component form. So the next thing we want to do is sketch this vector in standard position and determine the corresponding terminal point based on that sketch. So standard position means our initial point will be placed at the origin. Now, how do we find the terminal point? Well, we find it by expressing what this vector represents in terms of translation from our initial point. So the vector tells us from our initial point we have to move 4 units horizontally and -6 units vertically. Think of it kind of like slope, but it's slope that's been decomposed into a separate horizontal and vertical component. So from our initial point, we move 4 units horizontally, and then from there, -6 units vertically. And so this will be our terminal point. So we connect the dots with a line segment, but it's not just a line segment. We also have to indicate with an arrow which direction we're traveling in. That's going to tell us which point is initial and which point is terminal. So our initial point was at the origin, since we're in standard position. So this is going to be our terminal point, and we indicate that with an arrow pointing towards the terminal point. So if this is the way we graph the vector in standard position, that tells us the terminal point is going to be the point for -6. Now, alternatively, to show this algebraically, we'll do that with the next one. I'll show you how to do it algebraically. So we also want to sketch this same vector with a new initial point. So what if we were to put the initial point at 2, 3? So this is going to be our new initial point. Now, rather than just graphing the vector, I want to show you how you could find the terminal point algebraically. So we're starting at the point 2, 3. So 2 is our initial x-coordinate, and then 3 is our initial y-coordinate. Now, what the components of the vector tell us is how much we would need to add to each of these coordinates in order to get to the coordinates for the terminal point. So 2, 3, in order to get to the terminal point, that's going to be 2 with the horizontal component added on, and then also 3 with the vertical component added on, so plus -6. And that's going to give us the coordinates for our terminal point. So that's going to be 6, and then 3 minus 6 is going to be -3. So our terminal point will be at 6, -3. So 6, 1, 2, 3. And so that's going to be our vector with the new location. And again, initial to terminal, so we indicate that with an arrow. So notice all this is a translation of this original vector in standard position. So it has the same length, the slant is the same, we're pointing in the same direction, but we've translated it to a different location within the coordinate plane. So again, the actual expression of the vector is independent of where it is in the coordinate plane. These two vectors are considered to be the same. So some special kind of vectors that we often use that can also be used to indicate just horizontal and vertical displacement are what we call unit vectors. So in general, when you see the term unit in mathematics, unit means 1. So a unit vector is a vector that has a magnitude of 1. So certain applications require us to find a unit vector with the same direction as a given vector. So in other words, this particular vector has a specific length. Its length is not 1. Depending upon the situation, we may be interested in finding a vector that's pointing in the same direction but only has a length of 1 unit rather than this full length. So a unit vector in the same direction as another vector. Now, one thing to keep in mind is that any vector in the same direction as that given vector is going to be a scalar multiple of a unit vector. So in other words, a unit vector essentially summarizes a direction. It's the direction expressed in 1 unit of distance. So if we wanted to extend that vector, take another vector in that same direction, all we'd have to do is take that unit vector and multiply it by a scalar, multiply it by a constant. In other words, add on a coefficient. multiply those components by a coefficient. And so that would give us any additional vector we want that's going to take us in that direction. So we can kind of think of a unit vector as a vector just summarizing direction, where we're not focused on the size of the vector, just the direction that the vector is pointing in. So how do we find a unit vector for a particular vector in a given direction? Well, the first thing we're going to need to do is we're going to need to determine what is the magnitude of the vector that we have. If it's bigger than 1, well, what is it? If it's less than 1, what is it? What is the magnitude of the vector we're given? So magnitude for a vector, it's essentially going to look like the distance formula. It's going to look like the Pythagorean theorem. We've used this kind of equation frequently during our discussion of trigonometry. So if we want to take the magnitude of a vector, v, and we know its components, so we're going to assume we have components a and b, we'll call them a and b. The magnitude, or the length, of the vector is going to be the square root of a squared plus b squared. So keep in mind, this is going to be a positive number. We take a square root, we have a positive output. Magnitude, length, distance, always going to be positive numbers. So that's going to be the length of the actual vector. So for instance, if we wanted to take the magnitude of this vector, if we wanted to know how long it was, we square each of its components, add those together, and then take the square root. And that'll tell us what the distance is between the initial point and the terminal point, regardless of where the vector is located. Well, if we want to then generate a unit vector, all we have to do is divide each of our vector's original components by the length. So if we divide each component by the magnitude, what we then generate is a new vector that has a length of 1. It's going to be in the same direction as the original vector, but it's essentially the same thing as taking this vector and just shortening it down so that it's only 1 unit in magnitude. So if we have a vector with components a and b, then the unit vector in the same direction of v, which is given as u with a subscript of v, so u stands for unit vector. The subscript of v tells us we're looking in the direction of that original vector v, has the following components. So we're going to start with the original components for the original vector, but we're going to divide them by the magnitude of that vector. So divide each of them by the magnitude of the vector, and the new vector you have has a magnitude of 1. And you can check this by then taking these two coordinates, these two components, plugging them into the magnitude formula, and you can show that you get a magnitude of 1. So let's do an example finding a unit vector. Okay, so we have a new vector. We're calling this vector w, and w has a horizontal component of -3 and a vertical component of 2. So we want to find the unit vector that points in this direction but only has a length of 1, and we want to write it in component form. So the first thing we need to know is how long is the actual vector we're looking at. In other words, what is the magnitude of the vector w? So I'm going to take my two components, square each of them, and then sum their squares, and then take the square root of that, which is just the distance formula. It's the distance from one point to another, and again, that's expressed individually, horizontally and vertically with these components. So let's simplify that down. Okay, so -3 squared is going to be 9, and 2 squared is going to be 4. So that's the square root of 9 plus 4, which is the square root of 13. Now that can't be simplified. The only perfect square that divides into 13 is going to be 1, and we can't do anything special with the square root of 1. So that's as simple as it's going to go. Now keep in mind, you may end up with a distance that can be simplified further, and so you do want to simplify it if that's the case. So our unit vector in the direction of w is going to have the same horizontal and vertical component, but we're going to divide each of those components by the magnitude of W, which is then going to take that vector and it's going to shrink its magnitude. So my first component is going to be -3 divided by this distance. So -3 divided by √13. And then my second component is going to be +2 divided by √13. Now, as you've guessed at this point, we can't leave it like that. We don't leave things irrational, or non-rationalized, I should say. So we need to rationalize that. So -3 times the square root of 13 divided by 13, and then 2 times the square root of 13 divided by 13. So that's going to be our unit vector. Now let's verify, at least this one time, that this is in fact a unit vector. So it's going to point in the same direction as W because it was generated as just a multiple of each of those original two components. But is this truly a unit vector? Does it have a length of 1? We can check this by taking its magnitude. So if we were to square each of these components, sum them, and then take their square root, so that's going to be -3 times the square root of 13 over 13 squared plus 2 times the square root of 13 over 13 squared, and then we're going to take the square root of all of that. And this is a great time to use your graphing calculator. Save yourself a little bit of time. Now don't try to graph, or don't try to put all of this in one line. Go step by step, break it down. So just start by squaring each of these things. So the first thing we have is -3 times the square root of 13, and then that is divided by 13, and we are squaring that. So that simplifies down to this value. Can it actually be converted to a fraction? Let's see. Sure enough, 9 over 13. So that is going to simplify a little bit at a time, 9 over 13. Okay, let's do the same thing for the next one. So we have 2 times the square root of 13. That's divided by 13. And then we're squaring that. Okay, let's see if we can convert it to a fraction. Again, it converts, and it's going to be 4 over 13. So 9 over 13 plus 4 over 13, well, 9 plus 4 is 13. So 13 over 13 is going to give us 1. So we have the square root of 1, and we know the square root of 1 is just 1. So the magnitude of this vector is in fact 1, and so this is going to be the unit vector in the direction of our original vector W. So we can complete this process for any vector pointing in any direction with any particular length. Now we also have two special unit vectors that we can also use to represent just vectors in general. So they are the vectors, what we call I and J. So each of these is a unit vector, but it's a unit vector that's very, very specific. So the vector I is going to be the vector that has a horizontal component of 1 and a vertical component of 0. So if you picture what that were to look like in standard form, if you're starting at the origin, we travel 1 unit horizontally and then no units vertically, which means the vector in standard position would lay along the x-axis. Now J is going to be the vector that has a 0 horizontal component and a 1 vertical component. And again, if you were to graph that in standard form, starting from the origin, 0 units horizontally, 1 unit vertically, which means it would lay upon the positive y-axis. So these are special because they're unit vectors in the direction of the positive x and y axes. In other words, the vector I expresses motion by 1 unit just in the horizontal direction, and the vector J expresses motion by 1 unit just in the vertical direction. So if we were to combine some amount of movement horizontally with some amount of movement vertically, then that's another way of expressing the same thing we express with component form. So component form tells us this is how much we move horizontally, this is how much we move vertically. Well, we also can think of that as multiples of our individual unit vectors. So every other vector can be expressed as a combination of I and j. I, again, just summarizing horizontal movement, just a vector in that direction, and j summarizing vertical movement. So if our vector in component form is given with the components a and b, then another notation for this vector would be a, the horizontal component, times the vector I, the unit vector in the horizontal direction, plus b times the vector j, the unit vector in the vertical direction. Now in this case we call a the scalar horizontal component and b is the scalar vertical component. And so if we were to take each of these individual scalar values, multiply them by these individual vectors, that says take this single unit traveled in the horizontal direction and extend it by this much. Take this single unit traveled in the vertical direction and extend it by this much. Take motion in the horizontal direction, take motion in the vertical direction, combine it together, and you get motion diagonally, both horizontally and vertically. So if we have component form and we want unit vector notation, it's just a matter of making these values coefficients, scalar multiples of each of our individual unit vectors. So this vector given in component form, if we wanted it in terms of I and j, that's just going to be -3 times I plus 5 times j. It's as simple as that. So both of these notations express the same thing, just in a different way. Now, same rules with finding an additional unit vector. So we talked about how you can find a unit vector for something that's given in component form. We can also find a unit vector if our original vector is given in terms of I and j, because again, just think of I as summarizing horizontal movement and j as summarizing vertical movement. So the rules for finding magnitude, they apply. The rules for finding a unit vector also apply. So suppose this is our vector given in terms of I and j. So the vector v is -11 times I plus 60 times j. And we want to find a unit vector that's in this particular vector's direction, that points in the same direction but only has a distance, a length of 1. And we want to write in unit vector notation, which just means in terms of I and j. That's what that means. Well, we know first we need to find the magnitude. How long is this actual vector that we're looking at? That's the question. So keep in mind, this is now A and this is B. They're not given in those angled brackets. They're given as multiples of our horizontal unit vector and our vertical unit vector. But we treat them the same way in terms of how they apply in the magnitude formula. So -11 squared plus 60 squared. And let's do this one in the calculator. And this one we can probably plug in all in one line. Just make sure you use your parentheses carefully. So -11, and we're squaring that, that's under the square root, plus 60 squared, and that's under the square root as well. So believe it or not, this simplifies down really well. That's because -11, 60, and 61 represent a Pythagorean triple, or more specifically 11, 60, and 61. So this is going to be 61. This is the distance it would take to travel from any initial point to any terminal point if we followed the components of this vector. So if this vector has a length of 61 units, then we can take each of the individual components, divide them by 61, and that will give us something that points in the same direction as this vector, but only has a length of 1 unit. So the unit vector in the direction of the vector v is going to be given by -11 over 61 in the horizontal direction, so multiplied as a scalar multiple of our vector I, plus 60 over 61 multiplied by the vector j. And again, it's worth double checking, is this in fact a unit vector? Does it have a length of 1? And this is another good time to use the calculator and just plug it in. So if we were to square each of these values, sum those squares and then take the square root, in theory we should get 1. Make sure you use parentheses. So -11 divided by 60, and we're squaring that, plus, not 60, I'm about to make a mistake. Let's delete that, that should be 61. And then I'm going to go close parentheses, and there we go. Okay, and then 60 divided by 61, and then that's being squared as well. And then we're taking the square root of all of that. Oops, delete, there we go, press enter. And sure enough, we do get 1. So the magnitude of this vector is 1. And because the original components are still represented, just divided by this constant number, we're pointing in the same direction as we originally were. So we've kind of hinted at some algebra here that we haven't officially formalized. This idea of multiplying a vector by a number, by a scalar number. We've added vectors together. So let's formalize that kind of procedure a little bit more. And what your intuition tells you is probably going to be the case in terms of how things like this would be added. If we can break it down into components and we want to add something in components, well, the components add together just like we would expect. But we do want to formalize that a little bit more. We also want to talk about what would happen graphically if we're going to add or subtract vectors. So suppose we have two vectors. So vector v has components a1 and b1. And vector w has components a2 and b2. And we're going to define c as just some real number, not equal to 0 in this case. So c is just a scalar constant. So first, if we want to add two vectors together, the component form of vector v plus vector w, it does exactly what you would think it would do. So in component form, we can add the two horizontal components, the ones that correspond to one another, and then we can add the two vertical components, and that will give us the sum. So a1 plus a2, add the two horizontal components, and then b1 plus b2, add the two vertical components. And keep in mind, when we add these two together, we generate a new vector whose components are the sum of the individual vector's components. Now, from a graphical standpoint, what does vector addition look like? How do we model that? You're going to place v and w tip to tail, which essentially means we're going to graph v, and then where v ends, that's where we will start w. That's where we'll place the initial point for w. So again, remember, vectors are independent of their initial point. So we can move a vector around, we can place it anywhere we want. As long as the components are the same, we can have a vector any way we want and it doesn't change the vector. So place v such that v is graphed and then w's initial point starts where v ends. And then you're going to follow the path from the initial point of v, where you truly started, to the terminal point of w, the last point that you graphed. So let's just model what this would look like. So suppose we have an initial point right here, an initial or a terminal point right here, and suppose this is our vector v. And it looks like I've drawn something horizontal. It doesn't have to be horizontal. It can be any vector in any direction. So this is our vector v. Now suppose vector W is then maybe pointing in a different direction. When we place vector W tip to tail with V, we're going to let the initial point of W be where the V vector ended. So suppose this is our next terminal point if we were to graph the vector W. So we place the initial point of W where V ended, and then we travel to the new terminal point based on the components of W. If this is V and this is W, then the sum of the two vectors is generated by starting at the initial point of V and then traveling all the way to the terminal point of W. In other words, the path, the diagonal path it would take to go from one to the other, that is going to be the vector V plus W. So this vector right here, new vector, is the sum of V plus W. Okay, so if that's vector addition, what does vector subtraction look like? It's going to be very similar from a graphical standpoint with one change. Now in terms of the components, again, if addition works one way and it's an intuitive way, subtraction works the same way as well. So we're just going to subtract the individual components. So subtract the horizontal components, subtract the vertical components. Now from a graphical point of view, we're going to treat a subtraction as an addition, but we're adding V and negative W. In other words, negative W, we think of that as the vector with the same magnitude or length as W, but the opposite direction. So think of taking the slope, if you want to think of it like slope. We have the slope of W, it's pointing in one direction. Think of taking that slope and pointing it in the exact opposite direction. So still graphing tip to tail, but now we're graphing in the exact opposite direction from where W is generated. So again, let's draw a picture of what that would look like. And just to show you that it doesn't matter how things are set up, we can graph any way we want. Suppose this is our initial point and our terminal point for the vector V. And let's just say V points in this way. Let's be different. So this is going to be the vector V pointing in that direction. Now suppose the vector W, if we were to add, suppose W takes us right there. So if we go tip to tail, this is the terminal point for W. And so again, if we wanted to add, this would be V plus W. So tip to tail following that path, this would be V plus W. If we want to subtract, we go tip to tail, just like we did before, but instead of plotting W, we're going to plot W pointing in the opposite direction. So I'm going to try to draw the same length. It's going to be a vector of the same length, but pointing in the exact opposite direction. So we'll pretend that that is the same length. It's roughly the same length. This would be the vector negative W. So if this is W, it has a particular length, it's pointing in a particular direction. Negative W has the same length, but it points in the opposite direction. And so the vector we would get if we connect that initial point and terminal point, that is going to be V minus W. And notice something interesting happened here. Normally we think of addition as producing larger outputs and subtraction as producing smaller outputs. That's not necessarily the case if we're just talking about coordinates. In some cases, subtraction, suppose we're subtracting a negative. Well, subtracting a negative turns into an addition which produces larger outputs potentially. So in this case, V plus W is a shorter vector than V minus W. And I do need to put in the arrows, apologies. So there's going to be this arrow, and then this arrow would go right here. There we go. So in this case, the subtraction of the two vectors actually ended up larger, and that's just based on the path we followed to draw the two vectors and then trace from tip to tail. So that's going to be vector subtraction. And then our last operation we're going to do with vectors at the moment is what we call scalar multiplication. So as it turns out, we actually have a few different ways to multiply vectors. Here we're just going to talk about one way, scalar multiplication. So this is taking a vector and not multiplying it by another vector, but multiplying it as a scalar. In other words, providing a coefficient, if you want to think of it that way. So if we're multiplying our scalar, c, by this vector v, think of c as multiplying by each of these individual components. It's kind of like distribution. So we're going to multiply our scalar by each of the individual components for our original vector. And so what that's going to do is it's either going to take our original vector and it's going to lengthen it by a factor of c, or it's going to shorten it by a factor of c, just depending on whether or not c is greater than 1 or less than 1. And of course, if c is negative, again, that means we flip and we just point the direction in the opposite direction. So from a graphical standpoint, again, we're either going to stretch or we're going to shrink the vector v, but we don't change its direction. So this is essentially what we're doing when we use the unit vector notation with I and j. When we multiply I and j by a particular value, we're taking that unit vector, lengthening it by a particular factor or shortening it by a particular factor, and then same thing for j, either lengthening it or shortening it, depending on what our value for c is. So suppose v, and I'm going to use the actual ruler dimensions here. Suppose v, if we're talking about inches, is 1 unit long, and it points in a particular direction. Just for ease of graphing, I'm going to point it so that it appears to be horizontal. So we'll say this is the vector v. Well, suppose we wanted to graph 1/2 times v. Well, if we have a particular initial point, 1/2 times v is going to have the same direction as v. In other words, it's going to be a horizontal vector in this case. But if v originally was 1 inch long, then 1/2 v is going to be half that distance. It's going to be half an inch long. So this would be 1/2 v. Now what if we wanted, maybe we'll make something bigger, what if we wanted 3v, for instance? So again, we have an initial point, we're traveling in the same direction as v, but that 3 tells me we're going to take the initial length of v and we're going to triple it. So if v is 1 inch long, then 3v is going to be 1, 2, 3 inches long. Same direction, but triple the length. That would be 3v. So a scalar multiple is just going to shrink or stretch our vector, but not change its direction. Now, just to keep in mind, just as a note, what if we were to let c be 0? What if c were 0? The result of allowing c to be 0 and multiplying by our vector is we get what's called the 0 vector. So we could apply that operation the same way we do generally, but if we multiply these two components by a scalar factor of 0, then both components go to 0. Well, if we're talking about a vector that has both a 0 horizontal and vertical component, it means we start at an initial point and we don't actually go anywhere to get to our terminal point. So we would say that the magnitude is 0, and technically this vector has no direction. We don't actually move in any direction. The initial point and the terminal point coincide with one another. So the idea of a 0 vector is kind of strange, but just like the idea of 0 is initially kind of strange, the idea of nothing. Nothing can be used to indicate maybe that somehow things cancel out, something combines with something else and they reduce to zero. So we're going to use this idea of the zero vector to show that things are complementary to one another and that they combine together and sort of cancel each other out, just like we do algebraically. Okay, so let's do a little bit of practice with our operations, both algebraically and graphically. So we've been given that the vector v has components 1 and 4, and the vector w has components 3 and -2. So we want to find v plus w and v minus w in component form and unit vector notation, and then we want to graph each of them. Now, just as a reminder, graphing is independent of location. You can set any initial point you want. So you can graph from standard form if you want. You can graph anywhere you want on the coordinate plane. It's really up to you because we weren't given any guidance there. So v plus w means we're adding those two components together. So in component form, v plus w is going to take our horizontal components and add them, and take the vertical components and add those as well. So that's going to be 1 plus 3 for our new horizontal component, and then 4 plus -2 for our vertical component. And so that's going to give us a new horizontal component of 4, and then a vertical component of 2. Now, what if we want unit vector notation? That means I and j. That just means these are now the scalar multiples of I and j. So equivalently, we could write this as 4i plus 2j. Different notation, same idea. So what if we want to graph v plus w? Well, we're graphing v and we're graphing w tip to tail in order to model what's happening with addition. So for this one, let's graph it from standard position, which means I'm going to start my first vector at the origin. So from the origin, I'm going to graph the vector v, which says move 1 unit horizontally and 4 units vertically. So 1 unit horizontally and 1, 2, 3, 4 units vertically. And so it's going to be the directed line segment that starts at 0, 0 and then ends at 1, 4. That is our vector v. Now w is 3, -2, and if we line it up tip to tail, this is our new initial point for w. So the terminal point for v is where we're going to start the vector w. So the vector w says from the initial point, move 3 units horizontally and -2 units vertically. So 3 units horizontally and -2 units vertically, which is going to take us to that particular location. So that is going to be the vector w. And so if we start at the initial point of v and travel to get to the terminal point of w and find the diagonal path from one to the other, then that is going to be our vector v plus w. So this is going to be v plus w. Now again, that's assuming we graphed in standard position. If we had a new initial point for v, we would essentially have what looks like the same shape. It looks like we drew a triangle, because essentially we did. We would just have that triangle translated to somewhere else in the coordinate plane. Okay, let's now do v minus w, and maybe we'll graph it somewhere other than standard position. So v minus w, we're going to subtract their components. So horizontal components, v minus w, that's going to be 1 minus 3. And then for our vertical components, 4 minus -2. So be careful here with your signs. We're subtracting a negative. And so we simplify that down. That's going to be -2. And then 4 minus -2, that's going to turn to an addition. And that's going to be 6. So component form, -2 and 6. And then if we want unit vector notation, that's going to be -2i plus 6j. So let's graph this particular vector using this idea of vector subtraction. Okay, and let's start somewhere other than standard positions. So maybe we start at, I don't know, -2, 1. You can pick any initial point you want. Okay, so we're going to graph V first, starting from that position. So again, V says move 1 unit horizontally and then 4 units vertically. So 1 unit horizontally and then 1, 2, 3, 4 units vertically. If we connect our dots, that's going to be our vector V. Now, if we graph W, W graphs from there 3 units and then 2 units down. So let's graph W first, and then we'll do what we actually need to do for subtraction. So 3 units horizontally, and then -2 units vertically. And I'm just going to draw this in really lightly. This is not the actual one we want, but it's going to give us information about the one we want. Now, in order to subtract, we're not going to combine with W. We're going to combine with the version of W we would get if we traveled in the opposite direction. Well, what would that look like if we're talking about component form? Instead of 3 units horizontally and -2 units vertically, the opposite translation would be -3 units horizontally and then +2 units vertically. So -3 horizontally and then +2 vertically. That would be the actual vector that we're tracing to subtract. So that's going to be the actual vector that we want. And so V minus W is what we get if we connect our initial point to that final terminal point. So this is going to be V minus W, assuming we graphed starting at the point -2, 1. Okay, now it's worth paying attention to this. This is kind of interesting. We have our different forms for our 2 vectors, and we've graphed these vectors by actually combining the 2 original vectors. The components that we generate for our final answers should match up with what we see on the graph. In other words, if we were to just look at our resulting vector, we should be able to demonstrate that the components truly are 4, 2, and truly are -2 and 6. So for this particular vector, for our sum, the components are supposed to be 4 and 2. Well, notice as we trace the path and then connect to find that resulting vector, we've traveled 1, 2, 3, 4 units horizontally and 1, 2 units vertically. So sure enough, what we generate graphically matches up with what we generate algebraically. Now, same thing over here. When we subtract, we ended up with components of -2 and 6. So starting from our initial point, we move 1, -2 units, and then 1, 2, 3, 4, 5, 6 units vertically. So again, the graphical form of our vector matches up with what we expect from the algebra. Okay. Now let's just do a little bit of additional algebra, some slightly more complicated situations, just algebraically. Now you're probably wondering, where's all the trig in all of this? We're about to get there. Okay, so vector R is defined with components -3 and 8. Vector S is defined with components 2 and -5, and we want 2R minus 3S in component form. So 2R minus 3S. Okay, so what's going on here? We have 3 different operations, or maybe 2, depending on how we want to think of it. So we're multiplying the vector R by a scalar 2. We're multiplying the vector S by a scalar 3, and then subtracting. Or alternatively, we can think of S as being multiplied by a -3, which would change everything to an addition. It's really up to us how we want to handle that. So essentially, it's just order of operations and what's going to look a little bit like distribution. So we have 2 times our vector R, which is -3 and 8, minus 3 times our vector S, which is 2 and negative 5. So just as order of operations tells us that normal algebra, we have to do a multiplication before a subtraction, the same is true if we're doing these operations with vectors. So we need to multiply by these scalars before we can combine with addition or subtraction. So that means each of the individual components is doubled and then tripled in this case. And the result is going to be a new vector. So 2 times negative 3 is negative 6. 2 times 8 is going to be 16. And then I'm going to keep it as subtraction, and I'm just going to distribute the 3 or multiply by the 3. So 3 times 2 is going to be 6. And then 3 times negative 5, because keep in mind we're only distributing the 3, that's going to be negative 15. So if we want to then subtract, it's just a matter of combining matching components. So our first two components, the horizontal components, negative 6 minus 6, keep in mind they don't cancel, they combine. So that's going to be negative 12. That's our new horizontal component. And then 16 minus negative 15, which turns into an addition, that's going to be 31. So that is our resulting vector. Okay, what about one given in unit vector notation? Same idea, it just looks slightly different in terms of how we combine things together. So we want 3w minus 5v, and again we want that in terms of those unit vectors I and j. So let's write down the problem. So 3w minus 5 times v, and we'll just sub in our w and our v. So 3 times w, 6.2 times I, minus 3.4 times j. And I know it's tedious to write the arrows. You have to get in the habit of doing it though, because the notation is going to be important. And then v is going to be negative 1.7 I plus 2.2 j. Now this very much is distribution, whereas this only looks like distribution. This truly is distribution. So we're distributing our coefficients to each of these values. Okay, so 3 times 6.2, and if you want you can use the calculator of course. So 3 times 6.2, that's going to give us a scalar multiple of 18.6 times I. And then 3 times negative 3.4 is going to give us a scalar multiple of negative 10.2 for j. Now again over here we can either distribute a 5, or maybe in this case go ahead and just distribute the negative 5, and that way all the signs will have taken care of themselves. So negative 5 times negative 1.7 is going to give me 8.5, and now it's positive, so positive 8.5 as the scalar multiple of I, and then negative 5 times 2.2, which is going to be negative 11 as a scalar multiple of j. Now you can just think of it as combining like terms. I and j are not variables, but they can be treated as such in terms of simplifying all of this. So two terms that have I, you can combine those coefficients of scalar multiples, and then the same thing for the two terms that have a j. So for I, we have positive 18.6 plus 8.5, and so that's going to give us a total of 27.1 as our scalar multiple of I. Now for j, notice both of those coefficients are negative. So negative 10.2, and then from that we're subtracting 11. So negative minus 21.2 j. And graphically speaking, of course, we could represent all of these just as we did the previous examples. Again, keeping in mind that multiplying by those coefficients, by those scalar multiples, is going to take these original vectors and it's going to stretch them by a certain amount. Okay, so again, how does all the trig fit in here? Trigonometry is going to allow us to represent these vectors given in component form or in unit vector notation in a slightly different form depending on what kind of information we have. So it's going to allow us to take information about a vector and convert it into different forms. So what we have here, either using the angled brackets or using the unit vector notation, is individual horizontal and vertical components. So essentially the motion represented by the vector has been decomposed to the extent that we know exactly how much we move horizontally in relation to how much we move vertically. Keep in mind though, if we're looking at a vector in application, it's unlikely that we know components. More than likely, we know the amount, the magnitude of the vector, and we know the direction in which the vector is being expressed. So for instance, if you're talking about driving in your car, you could be driving 45 miles per hour northwest, okay, for instance. So 45 miles per hour is the magnitude of your velocity vector, and then northwest is going to tell the direction that you're traveling in. But that doesn't give you information about components for your vector. That would then have to be decomposed in order to look at just the horizontal component of your motion and just the vertical component of your motion. Trigonometry is going to allow us to do that. So it's going to allow us to take something either in component form and find the magnitude and the direction of the vector, or potentially in the other way, potentially a little bit more beneficially, to find the components given the amount of the vector, its magnitude, and given the direction in which the vector is being expressed. And this is going to look very similar to what we did with polar coordinates. Okay, the idea behind polar coordinates, converting between x and y, same kind of thing here. So sometimes we have the direction given as an angle, maybe not just northwest, but maybe we're given as an angle from a point of view, and then the magnitude of the vector rather than the component form, which is a little bit easier to work with. So if we want the component form, we're going to use those standard trigonometric relationships. So the idea is we want to take the direction and the magnitude, think of those as the things you've been given, and we want to find the resulting components. So what would we be given if we're given direction and magnitude? So suppose this is our vector, it's in the coordinate plane. It doesn't have to be something pointing this way, it doesn't have to be something graphed from standard position. This is just for ease of use. So we've been given the magnitude of our vector, which is going to be the directed distance to go from an initial point to a terminal point. And if we're given the direction, we're also given the angle that the vector makes from, again, what we think of as standard position. Well, we know every time we see something like this at this point that this represents part of a right triangle. It represents that right triangle. Well, what do these individual sides represent? Well, if we're talking about traveling from an initial point to a terminal point, this particular side represents the horizontal displacement to go from one point to another. We call that the horizontal component. We'll label that with A. And then this particular length represents the vertical displacement to go from the initial to the terminal point, what we refer to as the vertical component. So we'll call this B. So supposing that we know theta and the magnitude of our vector, how can we use that to find A and find B? Well, anytime we're looking at sides and how they relate to an angle, that comes back to our trigonometric ratios. So let's think about one that could be used for A. If we're given V, the magnitude of V, in other words, the hypotenuse of this triangle, and we have our angle, and we're interested in A, which in this case is going to be the adjacent side. Adjacent, hypotenuse, our angle, that's going to be related to our cosine. So cosine of our direction angle is defined as the adjacent side length, which is A, which is our unknown in this case, what we're interested in, divided by our hypotenuse, which in this case is the magnitude of our vector. Well, if that's the case, then the horizontal component, what we're interested in finding, is the same thing as the magnitude of our vector times the cosine of theta. When we were looking at polar coordinates, we called this x and we called this r. But otherwise, it's the exact same thing to convert from magnitude and direction, think of that as r and theta, to something involving x and y, which here we're just calling a and b. But otherwise, the relationships are all the same. Now, what about our vertical component? So we've got our direction and our magnitude, and we're interested in this particular side, which is opposite our angle. So opposite hypotenuse, our angle, we need our sine. So sine of theta is equal to our opposite side divided by the magnitude of our vector. And so that means our component is equal to the magnitude of our vector times the sine of theta. So those fundamental relationships right there are going to allow us to find our components given our magnitude and direction. So our relationships for magnitude and direction, we've already seen one of those. So the magnitude formula, the magnitude is going to be given by the sum of our components squared, and then we take the square root of that. And not surprisingly, if we know our components and we want to know the direction, we have the opposite, we have the adjacent, so we know the tangent of our direction angle is equal to our opposite over our adjacent. We've called them y and x, here we're just calling them b and a. And then our components, our horizontal component is given as the magnitude of our vector times the cosine of the direction angle, and the vertical component is given as the magnitude of our vector times the sine of our direction angle. And so if we were to put these two things together, if the goal is to find component form, which typically that's going to be the goal, to take our magnitude and a direction, what we can actually calculate a little bit more realistically in real life, convert that to component form, which is more easily to use algebraically, graphically. These are going to be our components. So the vector v in component form, if we think of our components as a and b, the first component is given as the magnitude of the vector times the cosine of our angle, and then the second component is given as the magnitude of our vector times the sine of our angle. So that's going to be our component form. And again, these are not completely new formulas. These are essentially the formulas we used to convert to polar coordinates, or to take polar coordinates and convert to rectangular coordinates. So think of your magnitude and direction like your polar coordinates. That's essentially what it is. It's a distance and an amount of rotation. And then our component form, that's more like our rectangular coordinates, our x and y. So let's do a couple of examples, finding these different values given one or the other, and then we're going to look at an application. Okay. So we want to write our vector in unit vector notation, ai plus bj, assuming we know, number one, our vector's magnitude, and number two, our vector's direction angle. So what does that mean? Well, we've been told that the length of the line segment, if we want to think of it that way, is 18. Think of this like 18 miles per hour. That's the amount, that's the magnitude of the vector. And then the 150 degrees tells us that starting from 0, we would have to rotate 150 degrees in order to get to the direction in which this magnitude is being expressed. So we want the components, the individual horizontal and vertical components, represented by this kind of motion. So it'll be helpful to think graphically before we start to look at the actual numbers. So if we're talking about a vector that has a magnitude of 18 and a direction angle of 150 degrees, we're talking about something in standard position that looks like that. where this is a length of 18. This is going to help us from the standpoint of recognizing whether or not our components make sense. So from standard position, if we have a vector that we graph in the second quadrant, we know the horizontal component should be negative and the vertical component should be positive. Is that going to happen? Well, we're going to see. So A, our horizontal component, is going to be the magnitude of our vector times the cosine of our direction angle. Well, in this case, the magnitude of our vector is 18, and our direction angle is 150 degrees. So we're taking the cosine of 150 degrees. Okay, so at 150 degrees, our cosine is going to be negative root 3 over 2. And so 2 divides into 18 9 times. So that's going to be negative 9 times the square root of 3. That is the horizontal component of this particular motion expressed in this direction. Now what about the vertical component? Well, again, we're going to have our magnitude multiplied in this case by the sine of our direction angle. So our magnitude is 18. We're multiplying by the sine of 150 degrees. And so that's going to be 18 times 1/2, which simplifies down to 9. So that's going to be the vertical component of this particular motion in this particular direction. So in unit vector notation, our vector v is given as negative 9 root 3 as a scalar multiple of the unit vector I. In other words, if this is 1 unit horizontally, this is the amount we travel horizontally. So in the negative direction, that particular amount. Plus 9 as a scalar multiple of the vector j. Sure enough, as we expected, the horizontal component is negative, the vertical component is positive, and that matches up with what we see here. Okay, let's go the other direction. So what if we have the components and we want to find the magnitude and the direction angle? Now here it says we can round to 1 decimal place, which tells me more than likely we're not going to have nearly as pretty numbers, which is okay. So our magnitude relationship tells us that the magnitude of our vector w is going to be the square root, where we take each of our components, square them, sum them, and then take the square root of that. So here, our horizontal component is negative 5, and our vertical component is 8. So that's going to be the square root of negative 5 squared plus 8 squared, all of that. And let's just plug this into the calculator. So 5 and 8 don't represent parts of a Pythagorean triple, which is why we know we're going to have to round. So we're taking the square root of negative 5 squared plus 8 squared, all of that. So to 1 decimal place, that's approximately 9.4. 9.4 units, whatever that happens to mean, whatever our unit is. So if we were to travel, for instance, from the origin using this vector, this would be the total displacement diagonally wherever we travel. So negative and positive, a negative horizontal component, a positive vertical component, means this would also be expressed in the second quadrant if we started at standard position. Now what's the direction though? Well, that's going to be helpful to think of, because if it's negative and then positive, it means we should have an angle somewhere between 90 degrees and 180 degrees. So our relationship for the direction, again related to what we saw with polar coordinates, is that the tangent is equal to the vertical component divided by the horizontal component. Well, in this case, B is going to be 8 and A is going to be negative 5. Now, how do we solve this? If this is a value that we can identify immediately from the unit circle, then we can just find the value for theta that way. But in this case, that's not going to help us because we don't see negative 8/5 anywhere on the unit circle. So that means theta can only be determined using our inverse tangent. So we're going to take the inverse tangent of -8/5, and that's going to give us an angle corresponding to this value of tangent. So we want to be in degrees. That's going to be more meaningful from a practical standpoint. So double check that your calculator is in degrees. And then we want to take the inverse tangent of -8/5. And that's going to give us, to one decimal place, approximately -58.0 degrees. So notice those double nines force us to round up to 0.0. Now, let's see if this makes sense though, because we said A was negative and B was positive. So starting from standard position at the origin, A is negative, B is positive, which would take us somewhere into the second quadrant. But this angle would take us into the fourth quadrant. So it's not the angle we want. The angle we want is the angle we would get if we added on an additional 180 degrees to this angle. So we're going to take this value and we're going to add 180 to it, and that's going to take us to another angle that has the same value for its tangent and meets our requirements. So to that we're going to add 180, and that's going to give us the angle we want. So approximately 122 degrees. That is going to be our direction angle. So this issue with quadrant, it's kind of a subtle issue, but it is important to think from time to time, what quadrant would you really be in, particularly from the standpoint of finding your direction angle. The angle you find has to be one that takes you to the correct quadrant, so it is going to be important to verify that that is the case. Okay, let's look at an application of vectors. How can they be used? As I mentioned at the very beginning, we're really just scratching the surface. Particularly if you take a physics class, you use vectors a lot. Vectors are used all the time, different kinds of vectors. So we're just going to look at one application, one that we can work with without needing a lot of physics context. So the application we're going to talk about is force, so vectors representing forces. So in certain applications in physics, lots of different applications, we encounter systems. A system just means a collection of events, different situation, things going on, where numerous forces are acting on an object. So we have the force of gravity. We also have what's called the normal force. So if something is sitting on the surface of the earth presses back up. That's what we call the normal force. Suppose gravity is acting, the normal force is acting, but maybe an object is being pulled or pushed in a particular direction. That adds an additional force. So all of those forces combine together to create this system of forces. So individual forces are vectors. They can be represented by vectors because they have both magnitude. Magnitude is again the amount, so the amount of force being applied, and direction. So the normal force applies vertically from the ground. Gravity, of course, pulls downward, and if you're pushing or pulling an object, you're pushing or pulling in a particular direction. So the fact that all of those vectors, all of those forces are being expressed in different directions means the combined, the net force, may be expressed in an entirely different direction. So if we look at all the forces acting on the system at one time, the combination, the sum of all of those forces, we call that the resultant force. Think of that as the net overall force. Certain things are fighting against one another. So what's the actual result of all of those forces interacting with one another? Now finding the resultant literally just means taking the sum of all the forces. If our forces, our vectors, are given in component form, finding the sum is pretty straightforward. We've seen how we can add vectors together, and that's exactly what we'll do. What if they're not given in component form? Well, we now know how to put them in component form. So we can do that, and then we can do exactly what we need to do to add them. So an extension A system of forces is said to be in what we call static equilibrium. The term equilibrium means balance. Static means not moving. It's in static equilibrium when the resultant force is the zero vector. Essentially, that means all the different forces acting on the object are canceling one another out. The system is balanced and the object is not moving in any particular direction. So let's put all of this together. What we now know about finding components from magnitude, from the direction angle, and this idea of all of these forces being summed up to give the resultant force. Let's put this in application. Okay, so three forces, F1, F2, and F3, are acting on an object. So it looks like it's a box. Notice it's in there, it's on the diagram, it's standard position, and that's just for convenience. If the magnitude of force 1 is 60 pounds, the magnitude of force 2 is 100 pounds, and the magnitude of F3 is 85 pounds, we want to write the resultant force R in terms of I and J. In other words, what's the overall net force acting on this object if all of these forces are competing with one another? And we want to round each of the individual components to the nearest tenth of a pound. And then finally, we want to determine what additional force would be needed to bring the system into static equilibrium. In other words, if there is in fact some motion that the object is undergoing, if all of these forces have combined in a specific way and the object is moving, well, what additional force would bring everything into balance and stop the object from moving? Okay, so we have our three forces. Let's write in the magnitude for each of them. So force 1 is 60 pounds. So the magnitude, the length of that line segment is 60, if you want to think of it that way. The magnitude of force 2 is 100 pounds. And the magnitude of force 3 is 85 pounds. So the greatest force is being expressed in this particular direction, which happens to coincide with the negative x-axis. Okay. So we need to put these into component form in order to determine how the forces are actually combining. So just looking at magnitude and direction angles individually, we can't determine the net effect on this particular object. We can do that if we have component form and we're comparing apples to apples, essentially. So each of these vectors needs to be put into its component form. Now we're going to have to be careful when we look at these angles. These angles are in relation to something other than the positive x-axis. But when we're talking about a direction angle, we're talking about an angle in relation to the positive x-axis. So the actual angles we're interested in are going to be that angle for this particular vector, this angle for this vector, and then this angle for our third vector. So we need to find those actual direction angles in order to determine what the components are going to be for our forces. So let's look at force 1 first. So for force 1, we know the magnitude is 60 pounds. What's the direction angle? Well, we know this particular vector makes an angle of 32 degrees with the negative x-axis, which means if we look at the whole 180 degrees minus the 32 to take us to the negative x-axis, that'll tell us what the actual direction angle is. So 180 minus 32, that means the actual direction angle from the positive x-axis is going to be 148 degrees. So once we have that, we can find our component form, and we're going to round to the nearest tenth. So we will have to round in this case. So our first component is going to be 60 times the cosine of 148 degrees. And then our second component is going to be 60 times the sine of 148 degrees. So let's evaluate those and round to the nearest tenth. Now let's double check, are we in degree mode? Yes, we are. So then we can just plug it in. So 60 times the cosine of 148, approximately negative 50.8 rounded to 1/10. And then 60 times the sine of 148 degrees, 31.8. Does this make sense? So based on where we are in standard position, this force is directed in this direction, so the horizontal component is negative and the vertical component is positive. So that does make sense in this case. So if we want to write it as one force in terms of I and J, that's going to be negative 50.9 times I plus 31.8 times J. That's going to be force 1. Okay, now we need to do the same thing for the remaining two forces. So force 2 has a magnitude of 100 pounds. And we know that it's oriented along the negative x-axis, which means it's 180 degrees from where we initially start. So its direction angle is going to be 180 degrees, which means finding the components is going to be pretty straightforward. So A is equal to 100 times the cosine of 180 degrees. Well, the cosine at 180 degrees is going to be negative 1. So 100 times negative 1 is negative 100, and that's exact, it's not rounded. Now you can probably guess what the vertical component is going to be just looking at the picture. If we're only moving horizontally and not moving vertically, what can we say about the vertical component? Well, let's verify that algebraically. So 100 times the sine of 180 degrees. The sine at 180 degrees is 0. So 0 times 100 is going to be 0. So this particular force, as indicated by this graph, is only applied in the horizontal direction. There is no vertical component. So when we write the unit vector notation, we only have a multiple of I. We don't actually have a multiple of J. Okay, and last but not least, force 3. And again, we have to determine the actual direction angle. We know the magnitude is 85 pounds. And then we travel 270 degrees to get here. And then the angle between our actual vector and then the negative y-axis, that's 18 degrees. So 270 degrees and then the additional 18, 270 plus 18 is going to be 288 degrees. So that's our direction angle. Now when we find the components for this one, based on how it's oriented in standard position, the horizontal component should be positive and the vertical component should be negative. Okay, so our horizontal component is going to be 85 times the cosine of 288 degrees. So we want to evaluate that. So 85 times the cosine of 288 degrees. That's going to be 26.3, which is positive as we expect. And then the vertical component, 85 times the sine of 288 degrees. Negative 80.4, and again it's negative as we expect. So in unit vector notation, that's going to be 26.3 times the vector I minus 80.4 times the vector J. So now that we have all three of these vectors represented in component form, what do we want? We want the resultant force. As soon as I see resultant force, that means the sum of F1, F2, and F3. The resultant force is the net force acting on this object if we sum all of the forces. Well, now that they're in component form, that's just a matter of adding up all of the matching components. So our resultant force is going to be the sum of these three forces. So F1 plus F2 plus F3, and I've gotten sloppy. I need to write my arrows. Just get in the habit now. Make sure you always write them so we know we're talking about vectors and not scalars. Okay, and rather than rewriting these, we're just going to add up everything that's like. So all of the i's, all of the j's. So for force 1, force 2, and force 3, for the I, the horizontal component, we have negative 50.9 plus 100 plus 26.3. Add all that up and we get 75.4. So 75.4 times I. Oh, excuse me, this should be negative 100. Apologies. This should be negative 100. Let's try that again. So negative 50.9 minus 100. There we go. And you probably already noticed that and you know I was making a mistake. Plus 26.3. There we go. So it's going to be negative 124.6 times I. Okay, let's double check the j's. Yep, those look good. So let's do that. So our j's, we have 31.8 for F1 and then negative 80.4 for F3. And notice again, F2 doesn't have a vertical component. It was entirely horizontal. So minus 48.6 times J. That is our resultant force. That tells us what's actually happening with this object based on all of these forces being expressed. So we have a negative I, we have a negative J. So what does that actually mean? It means if we were to actually look at this object and assume it was in motion, because I and J are both negative, this object is actually moving in this direction. It's moving horizontally in the negative direction and vertically in the negative direction as well. So it's actually moving something like that. So then the question is, what additional force would be needed to bring the system into static equilibrium? In other words, if this is the net force and our object is moving in this direction, what additional force would need to be exerted to stop the object and balance the system? So I'm just going to call this SE. What would we need for static equilibrium? Well, we would need whatever it would take to balance out the I and J, the horizontal and vertical component, and bring everything to zero. Well, if our horizontal component is negative 124.6, we would need a total of positive 124.6 in the horizontal direction to balance the horizontal motion. And then if our vertical motion, negative 48.6, we would need positive 48.6 to bring that into balance. So this additional vector, this additional force, would bring the system into static equilibrium. It would balance everything out, and then the object would be motionless. Okay, so I want to talk about one more thing related to vectors before we wrap it up. So we've talked about one type of vector multiplication, and as I mentioned at that point, there's not just one type, there's actually a few different types of ways that we can multiply a vector. So we can multiply a scalar by a vector, and the result is another vector. We know multiplying a scalar by a vector is either going to stretch that vector or it's going to shrink it. If we multiply by a negative, that's going to point the vector in the opposite direction. There's another way of multiplying vectors, not the scalar multiple, but what we call the dot product. So the dot product is going to require that we actually multiply two vectors together, but it's going to give us an interesting result. So again, scalar multiplication involves multiplying a vector by a scalar, which results in another vector. The result of multiplying by a scalar is a new vector in the same direction as the original vector. Now, an additional form of vector multiplication, actually multiplying two vectors together, is what we call the dot product. And when we take a dot product, the result is not a vector, it's actually a scalar. It's going to be a scalar involving the components for our two vectors that we're multiplying. So not surprisingly, dot product, we write a dot, which is one of our symbols for standard multiplication. Now we have to be careful with the notation here because we also have something called a cross product, which we will not look at. But we have to be careful about the notation for multiplication. You don't want to use the dot unless you're talking about a dot product. So if you're multiplying by a scalar, you don't want to actually write a symbol between your scalar and the vector in order to avoid that confusion with this, what we're calling the dot product. So when we take the dot product of v and w, we're going to multiply the two horizontal components together, so a1 times a2. We're going to multiply the vertical components together, so b1 times b2, and then we're going to add the result of that. So we're just multiplying the scalar components of these vectors, and then we're adding those two results together, and so the result is going to be a scalar. Now what does this actually mean? We'll talk about that in a minute. Why do we even do this? There is a particular reason. So given two vectors, let's find a few different things. So v dot w, the dot product of v and w, that's going to be multiply these two components, multiply these components, and add them in that order. So a1 times a2, that's going to be 3 times negative 2 plus negative 7 times 5. And of course, as always, we can just do that in the calculator if we want. So 3 times negative 2 plus negative 7 times 5, and that's going to give us negative 41. Now, what if we take the dot product of w times v? So that's going to be this component times 3. So that's going to be negative 2 times 3. And then 5 times negative 7. What's going to happen when we do that? Well, again, if we want to just plug it into the calculator, that's going to be negative 2 times 3 plus 5 times negative 7. And notice we also get negative 41. And so we'll talk about this in just a minute. Now, what if we take a dot product of a vector with itself? That just means we're multiplying the first component by itself. We're multiplying the second component by itself. And then we're taking the sum as we did before. So that's going to be 3 times 3 plus negative 7 times negative 7. Well, another way to write that would be 3 squared and negative 7 squared, and then add those up. And so if we take 3 squared plus negative 7 squared, make sure the negative 7 goes into parentheses, that's going to be 58. Now, what is the magnitude of v? This is not directly related to finding the dot product, but we'll talk about why we're looking at this in just a second. Let's find the magnitude of v, and we know how to do that. We square each of the components, sum them, and then take the square root. So square root of 3 squared plus negative 7 squared. So that's going to be the square root of 9 plus 49, which is going to be the square root of 58. And that can't be simplified, we just leave it like that. So I want you to notice a couple of things that are happening here. First off, for A and B, all four of these lead us to two key properties of the dot product, things that we can say about the dot product in general. So from A and B, what happened? We multiplied v times w and then w times v, and notice the result was the same. This leads us to a property of commutativity. Commutativity means order doesn't matter. So the dot product is commutative, which means v dot w in that order is going to be the same as W dot V. The order isn't going to change anything. Standard multiplication is that way, addition is that way. We also have things that are not commutative. So subtraction is not commutative, division is not commutative. In those cases, order matters. So it is important to note that with the dot product, order does not matter. You can multiply in either order and nothing changes. We also have a relationship between the dot product and the magnitude of a vector. So notice in this case, this vector's magnitude was square root of 58, and the dot product of the vector with itself was positive 58, just as is. So this leads us to actually another definition for magnitude. So if you take the dot product of a vector with itself, that's the same thing as taking the magnitude of a vector and squaring it. Another way of saying that is that the magnitude of our vector is also the same thing as the square root of the dot product of the vector with itself. So that's just another way of defining the magnitude of a vector. We can also define it in terms of a dot product. Now, why does the dot product matter? Here's how we use it. So suppose we have two vectors, maybe like the vectors we had in the previous example. So maybe we were looking at just F1 and F3, and maybe we don't know the angle between them. Suppose we were given F1 and F3 not in magnitude and directional form, but in component form. Suppose we were given their components. It's possible that we'd want to know the angles between those two vectors in order to indicate how they interact with one another. The dot product is going to allow us to find the angle between two vectors. So this is the relationship. If theta is the angle between two vectors, what we're calling V and W, then the cosine of theta can be defined in terms of the dot product. So the cosine of theta is defined as V dot W divided by the magnitude of V times the magnitude of W. So the numerator is a scalar. Each of these magnitudes is a scalar. So this is just one ratio of two scalars. The cosine of the angle between our vectors is equal to this particular value, which means the actual angle, if we want to solve for it, is going to be the inverse cosine of that value, whatever that value happens to be. So dot product of V and W divided by the magnitude of V times the magnitude of W. And we're not going to have any issues like we had with the law of sines where maybe we don't get the right angle, something like that. In general, this will give us the angle we need between our two vectors. So let's use this formula in order to find the angle between two vectors, given in component form. Keep in mind, if they're given in terms of their direction angles, this is not necessary. We can determine just based on how their direction angles relate to one another. But if our vectors are in component form, this is going to be one option for determining how they relate to one another. So we want to find the angle between this V and this W, where V has components -4 and 3, and W has components -6 and -2. And we want to round to the nearest tenth of a degree. Well, we know the cosine of our direction angle is going to be the dot product of these two vectors divided by the magnitude, and I wrote them in the opposite order, but it's going to be okay, same thing, by the magnitude of each of them. Now, rather than trying to just plug everything in and simplify it all in the big expression, I recommend go out to the side and calculate each of these values. So find your dot product, find V dot W, find your magnitude for each. So V dot W, we're going to multiply our horizontal components, multiply our vertical components, and then take the sum of that. So that's going to be -4 times -6 plus 3 times negative 2. So negative 4 times negative 6 is 24. 3 times negative 2 is negative 6. So 24 minus 6 is going to be 18. Okay, now let's find our magnitude. And ideally, because we're going to round at the end, we want to avoid rounding as much as possible near the beginning of the problem. So we'll see if we can avoid that. So magnitude of V, we're going to square our components, add them, and then take the square root of that sum. So negative 4 squared plus 3 squared. Now you may notice 4 and 3, those look familiar. There's a Pythagorean triple there. Let's verify that that is the case. So the square root of negative 4 squared plus 3 squared is going to be 5. So the vector V has a magnitude of 5. Direct vector W, similarly, square your components and then take the square root. So that's going to be negative 6 squared plus negative 2 squared, and then we take the square root. Now 6 and 2 don't represent a Pythagorean triple, so we're not going to be able to use the calculator here except maybe to simplify what's inside. So we have negative 6 squared, which is 36, negative 2 squared, which is 4, so 36 plus 4 is going to give us 40. And we can simplify that if we want, or just because we're going to plug in here and then plug all of it into the calculator, we can leave it like that if we want. If we want to simplify though, just for the practice, 40 is not a perfect square, but 40 is divisible by 4, which is a perfect square. So we can take the square root of 4, which is 2, and when we divide out that 4, we're left with a 10. So that's going to be the square root of 10. So now we just plug in these values to our formula. So V dot W is going to be 18, and then in our denominator we have 5, we have 2 root 10. So all of that means our angle theta is going to be the inverse cosine of whatever that value happens to be. And again, our denominator, 5, 2 root 10. Our numerator is 18. And so rounded to the nearest tenth of a degree. Now, technically you can type this in one line if you're careful, but I would go one step at a time. Start with whatever's inside your inverse cosine. So we have 18 divided by 5 times 2 root 10. Okay, so that's all in the denominator. So that's going to be the whole expression inside the inverse cosine. So there's that. Now we're applying the inverse cosine to this number. So I'm going to copy it from the previous line with second and negative, the answer operation. And then that's going to give us our angle. So 55.3 degrees, roughly. So that is going to be the angle between our two vectors. And again, if we knew their direction angles, which we could certainly find, we could find the angle that way just by comparing their direction angles. This is going to give us another option. So we can extend this relationship in order to create a new definition of the dot product, this relationship between this direction angle and the dot product and the magnitude of our two vectors. So if we know that the cosine of our angle is defined as the dot product divided by the product of our magnitudes. Suppose we wanted to solve for the dot product. In other words, think of a new way to define the dot product. If we were to isolate everything that's in the numerator, that dot product, how could we do that? Well, if we were to multiply both things in the denominator, that would move them to the other side. That would isolate the expression for our dot product. And so that would be equal to the magnitude of V times the magnitude of W times the cosine of the angle between them. So how does this relate? This is going to give us an interesting relationship between the dot product and our directional angle. So keep in mind, magnitude of V, magnitude of W, when we talk about magnitude, magnitude must always be positive. Magnitude is a distance. It's the length of our vector, the diagonal length, which can't be negative, so we always treat it as being a positive distance. So if these two values are both positive, and we're thinking of all of this as the definition for the dot product, well, the dot product can be both positive and negative. We've seen that. So this value was positive. The one we calculated on the first page, we got a negative dot product. So the dot product can be positive or negative. Well, if this is a definition of the dot product, and these two values are always going to be positive, that means the only way the dot product can be negative is based on what happens with the cosine, or more specifically, what happens with theta. So suppose our dot product is greater than 0. That means that this whole expression, of course, is greater than 0. Well, these two are positive. For the whole expression to be greater than 0, cosine must also be positive. So we know the cosine of theta would also have to be a positive value. Well, what does that mean for the actual angle theta? How would we get a positive cosine? That means, if we're talking about our quadrants, we're talking about the angle between two vectors, that means that we had to get an angle that was from 0 to 90 degrees. All of the angles from 0 to 90, not including 90, we're going to have a positive cosine. So that means 0 degrees is less than or equal to our angle, and our angle is less than 90 degrees. So it's somewhere within the first quadrant. Why wouldn't we look at angles that are anywhere else? Well, we're talking about the angle between two vectors. So suppose we had a vector here and then maybe a vector down here. We could say that they are a certain distance away. If we had something that's a little further away, so suppose we had a vector here and then a vector here, we'll just treat the angle between them as being this angle, the shortest angle between them. So the furthest any two angles can be from one another is 180 degrees. So we're not worried about angles from 180 to 270 or 270 to 360. The largest distance we can have, rotationally speaking, between two angles is going to be 180 degrees if they point in exact opposite directions. So if our angle is less than 90 degrees, our cosine is greater than 0, that means our dot product was positive, or vice versa. Now, what happens if our dot product was negative? Well, again, these two values have to be positive. So the only way the whole result from this expression could be negative is if the cosine was negative. So that means the cosine of theta has to be less than 0. Well, based on the fact that we can only have angles from 0 degrees to 180, what do we know if the cosine was negative? Well, the only way the cosine that could be negative is if we were between 90 degrees and 180 degrees. So that means 90 degrees is less than our angle, and our angle is also less than or equal to 180 degrees. For any angles within that interval, we know we're going to have a negative cosine, which means the dot product is going to be negative. So what's the only other possibility? Well, if our dot product is neither positive nor negative, but is equal to 0, what happened? Well, these are both going to be positive numbers. So the only way the whole dot product could evaluate to 0, since this is the expression for the dot product, if these two are positive numbers, the only way all of this could evaluate to 0 is if cosine of theta is equal to 0. Well, what do we know about the angle if the cosine is equal to 0? Well, if we're only looking at angles between 0 and 180, since that's the furthest amount we could take to go from one vector to another, the only angle that would result in a cosine of 0 would be an angle of 90 degrees. When we have two angles that are separated by 90 degrees, we have what we think of as a special case. So angles or vectors that meet at a right angle are considered to be special. We have a name for them. They are said to be orthogonal. So what does this mean though? This means that rather than finding the angle between two vectors, if we know the dot product of our vectors evaluates to 0, then automatically that means the vectors have to meet at 90-degree angles. So rather than having to take the time to calculate the entire value for our angle, if we were to just take the dot product between our two vectors, that automatically indicates that we have a 90-degree angle if our dot product is 0. So anytime we take the dot product between two vectors and get a result of 0, that automatically tells us that our vectors meet at right angles, and we say that our vectors are orthogonal. And again, this is a very special case. Specific things happen in the context of applied problems when we're looking at vectors that are orthogonal. So knowing whether or not our vectors are orthogonal is going to be helpful to determine. So let's wrap it up with a couple of examples. I know this has been a long video. So we want to determine whether each pair of vectors is orthogonal or not. Do they meet at a 90-degree angle or do they not? Now we can find the actual angle between them, but all we need to do to make this determination is to find the dot product. If the dot product is equal to 0, then the vectors are orthogonal. If the dot product is anything other than 0, then they're not orthogonal. So if we take the dot product of V and W, let's see what we get. So for this pair, we have 3 times 8 plus -6 times +4. So 3 times 8 is going to give us 24. And then -6 times 4 is going to give us -24. And then 24 minus 24 is equal to 0, which implies that yes, these two vectors, were we to graph them or look at them in context, those two vectors are orthogonal. They do meet at a right angle if we graph them with the same initial point. Now what about these two? Let's try these two. So what is the dot product of the vectors S and R? So multiply their horizontal components, so -2 times -4. Then add on the product of their vertical components, so -5 times 8. So -2 times -4 is going to give me +8. And then -5 times 8 is going to be -40. All we care about is the fact that this is not 0. So technically this is -32. But all we care about is the dot product 0 or is it not 0? In this case, it's not 0, which implies that these two vectors are not orthogonal. Okay. So we talked about a lot in this video. We talked about a lot in this section. And again, honestly, this barely scratches the surface of what you can discuss with respect to vectors. Vectors, it's a very broad topic. Again, you'll look a little bit more at vectors when you get to calculus. If you take a physics class, you also use vectors a lot, so you'll talk about vectors in more detail. But being able to convert vectors between different forms is going to be the big takeaway here. So if we have magnitude and direction, how do we find the component form of a vector? If we've got the component form of the vector, how do we find the magnitude and direction? This is where the trigonometry comes into play, doing those kinds of conversions, which may be helpful within certain applications.